And it says the Andromeda Galaxy is speeding toward our galaxy at 300,000 miles per hour. The example of blue shift. We looked at the Hubble-Lemaitre law that showing that most of the galaxies appear to be redshifting, meaning they're moving away from us. And also the farther away from us they are, the faster they are moving away from us. And a little closer look at George Lemaitre. He's a Belgian astronomer, and this is a cartoonist who definitely knows their astronomy history. In using the name, Professor Lemaitre prepares to demonstrate his Big Bang theory. There is Professor Lemaitre and Einstein on the right. So now your previous observation and current one, you've learned that Einstein only stands on the right in pictures. Just kidding. This is Max Planck giving the Nobel Prize to Einstein you saw earlier. So Lemaitre and Hubble here have recognized the fact that galaxies are redshifting away from most of the galaxies. And one of the ways we often see this demonstrated is through people using balloons. So a classic demonstration of showing the expansion of space is taking a balloon and putting dots on it with a marker, and then your instructor will force air into the balloon, showing that the balloon expands, and they'll say, look how the space in between expands, but not the dots themselves. Which is a little mind-boggling in that, I mean, if you look at these numbers here, those are definitely much larger, much clearer. The dots themselves tend to be slightly bigger. So that always kind of threw me, especially in university. And then one time I had a university astronomy professor who took a different approach. They had a balloon, and she had taped pennies to the outside of the balloon. Showed us how the pennies represent a galaxy when you force air through the balloon. It's the space between the galaxies being represented by the pennies that expand, not the pennies themselves. So this was much better than the marker. Look at the marker not increase in size, and yet it does. But then a penny fell off, and I kind of worried and wondered, where'd the galaxy go? Has it popped out of existence in a parallel multiverse? Wasn't quite sure. An alternate method is the raisin bread loaf example, how the raisins, a prime ingredient, will not increase during the cooking, and they might plump a tiny bit as galaxies do grow a bit, increase in mass ever so slightly, but it's the space between the galaxies that increases or expands, just as the space in the rising bread in cooked bread will increase. And with the Hubble-Lemaitre law, you can actually predict this set ratio of galaxy expand, or the space between galaxies expanding. So the raisin loaf bread, a little bit better example than the balloon, that it's the space between galaxies that is doing the expanding at predictable amounts, measurable amounts and ratios, not the galaxies themselves. One of the best demonstrations for the universe expansion is demonstrated here with, this is an elastic, piece of elastic, and then attached to the elastic are stars that represent galaxies, so that when you pull on the stretchy elastic fabric, you clearly see it's the space between galaxies that do the expanding, not the galaxies themselves. And also, it's a great demonstration that if you were to watch this star that's representing a galaxy, as that elastic is being pulled, it appears this galaxy is moving away from this star. This galaxy appears to be moving away from this galaxy. If I were looking at this galaxy, from my point of view here, looking out, this galaxy is moving away from me. This galaxy moving away from me. So another way to demonstrate that idea we've looked at before, that no matter where you are in the universe, you appear to be the center of the universe. And of course, there is no center to the universe. And the person with this great demonstration of the universe expansion is one of the mappers of our universe. It's Margaret Geller. Previously, we looked at our supercluster, Laniakea, and we looked at the superstructure in the new evidence and how we were mapping these. And we're going to play out the rest of that video for you. And of course, play the beginning again to refresh.
Somewhere in the universe is a small blue planet, the third rock from a star called the Sun, just one of billions of stars in a spiral galaxy known as the Milky Way. But where in the universe is the Milky Way? A team of scientists gathered data on more than 8,000 of the galaxies that surround us. They mapped each galaxy's position and movement in space. And, for the first time, they've shown that the Milky Way is part of a much larger system of galaxies, a supercluster that they have named Laniakea. The Milky Way is nested in the furthest reaches of this structure, on the outskirts. The entire universe can be seen as an intricate network of galaxies, a cosmic web. Some areas are almost empty, dark voids. Others are densely packed with galaxies in regions known as superclusters. Superclusters are the biggest structures found in the universe, but scientists have struggled to define where one ends and another begins. To map our home supercluster, a team led by Brent Tully at the University of Hawaii studied the motions of the galaxies around us in unprecedented detail. Even though the entire universe is expanding rapidly, gravity is also at work, pulling against this acceleration. By discounting cosmic expansion, the team worked out which galaxies are being pulled towards us, shown in blue, and which are being pulled away, shown in red. This enabled them to create a map of cosmic flows, the paths that galaxies migrate along, tugged at a tiny pace by the force of gravity. Using this motion, they came up with a new way to map the distribution of matter in the universe. Delving into our home supercluster, you can see that most galaxies are being pulled towards a dense centre. This is known as the Great Attractor. Our galaxy is among those sliding towards this patch of space, which dominates our region of the universe. Let's take a different view. Each circle represents a galaxy. Again, we can see most galaxies being pulled towards the Great Attractor in the direction of the arrows. Between the Great Attractor and us, the Milky Way, there's a relatively empty area, a blue void. And next to us is Virgo, a large and dense cluster whose bright galaxies have been observed from Earth for centuries. Until now, astronomers grouped us, the Milky Way and its surrounding galaxies, with Virgo and nearly 100 other clusters in a supercluster that stretches 100 million light-years across. But using this new technique, we can see that this is just the tip of the iceberg. This cluster of clusters is merely an appendage of a much larger supercluster, more than 100 times bigger and more massive. But how did the team know how to redraw the boundaries of this cosmic map? Here's our supercluster in black, and a neighbouring structure, Perseus Pisces, in red. Scientists defined the boundary as the points where the flows of galaxies diverge, like water dividing at a watershed. This is where neighbouring structures shear apart. This is the first clear definition of a supercluster. Laniakea means immeasurable heaven in Hawaiian, a fitting name for the vast community of galaxies that we are a part of. So now we know that on the edge of a supercluster called Laniakea, in a galaxy called the Milky Way, around a star we call the Sun, there is a small blue planet, our home.
Cosmology is most certainly a fascinating and intriguing part of astronomy to study. Since we've explored a tiny bit of this expansion of the universe, we now can actually address Olber's paradox. Remember the why is the night sky dark? Because it shouldn't be, but it is. Here is our Minute Physics friend to share with you a reasoning for why is the night sky dark.
Why is the sky dark at night? You might think the answer is obvious. The sun isn't up, but the only reason the sky looks blue during the day is that sunlight scatters off of the atmosphere. If we didn't have an atmosphere, like on the moon, the sky would always be dark, even when the sun is shining. So let's rephrase the question. Why is space dark? I mean, space is full of stars, countless stars which are all about as bright as the sun. And in an infinite eternal universe, no matter what direction you picked, if you looked far enough in that direction, you would see a star or galaxy. So the whole sky should be as bright as the sun, night and day. And since it's not, does the darkness of the night sky mean that there's some distance away from us when stars and galaxies just stop? A boundary between something and nothing? An edge to the universe? Not exactly. All of our evidence seems to indicate that space has no edge, but the universe itself does. Not a spatial edge, but a temporal one. As far as we know, the universe had a beginning, or at least a time about 13.7 billion years ago when the universe was so small and crumpled up with itself that our standard notion of space and time breaks down. And since only a finite amount of time has passed since this so-called beginning, that means that some of the stars necessary to fill up the brightness in every direction are so far away that light from them plain hasn't had time to reach us yet. It's as if the universe were a big thunderstorm, and we're still waiting to hear the thunder from the really distant stars. But wait, it's better than that. Since light takes time to travel across the universe, when we point our telescopes at something really far away, we're actually seeing that part of the universe as it was when the light was emitted. So when we look at 13.5 billion-year-old light, it's not that we don't see stars just because the light from them hasn't gotten to us yet. We don't see any stars because we're getting a peek at the universe before any stars had formed. A starless universe. Now that sounds to me like a pretty good reason why we look up and see a dark night sky. But it's not. I mean, it is true that we can find points in the sky where there aren't any stars by looking past the earliest stars and thus farther back in time. But even when we point our telescopes past the earliest stars, we still see light. Not starlight, but the light left over from the Big Bang. We detect this cosmic background radiation coming more or less evenly from all directions, forming a background beyond the stars. So I guess the night sky isn't actually dark to begin with. Right, so if our telescopes tell us that the night sky isn't dark, then why does it look dark? Here's a clue to the real answer. When the Hubble telescope photographed the distant stars of the astoundingly beautiful Hubble Extreme Deep Field, it took the picture using an infrared camera. Why? Well, distant stars and galaxies are moving away from us because the universe is expanding. So the same way a record slowing down lowers the pitch of my voice, the Doppler effect causes stars moving away from us to become redder. And the farther away they are, the faster they move away from us and the redder they become, until they become infrared. And then we can't see them anymore, at least not with our human eyes. And that's why the night sky appears dark. In summary, if we lived in an infinite, unchanging universe, the entire sky would be as bright as the sun. But the sky is dark at night, both because the universe had a beginning so there aren't stars in every direction, and more importantly, because the light from super distant stars, and the even more distant cosmic background radiation, gets redshifted away from the visible spectrum by the expansion of the universe. So we just plain can't see it. Finally, we've shed some light on why the night sky is dark, and why it isn't.
Now I'm going to turn you into the hands of a professional who will sum up the past 40 minutes or so of your life in about a minute.
So my name is Dr. Maggie Adair Pocock. I work as a rocket scientist for a company called Astrium Limited. The Big Bang is an amazing theory, but quite a complicated idea. And it all started with some observations made by a chap called Edwin Hubble. And here's the chap we named the Hubble Space Telescope after. Now, what Hubble did is he was trying to understand the size of the universe. He observed stars of a known brightness. They're called Cepheid variables. Now, when he did this, he noticed something very odd. Firstly, that some of these stars were far, far further away than we ever anticipated. And also he noticed their colours were slightly changed, shifted towards the red, something called redshift. So from Hubble's observations, we notice that everything seems to be moving away from us. The universe is effectively expanding. So as time goes on, the universe expands more and more. But let's say we reverse time and take time backwards. It means that if we go back in time, everything starts to coalesce and come together. And so this is how we came up with the theory of the Big Bang. The idea that the universe began with a cataclysmic explosion which created space-time and all the matter in the universe.
And remember that explosion is more of an expansion of space, not that explosion in space. My friend Dr. Mueller here with the Veritasium YouTube channel is going to do a nice wrap-up of the major points we've looked at with the high mass life cycle of a star and Big Bang nucleosynthesis.
Recently, I was in New Zealand asking the real tough questions. Like, where did the Earth come from? Like, what was it before it was the Earth? Like, how did it get here?
I did not want to do this anymore.
Those who were game to answer my question realized that an explosion was important to Earth's formation.
I suppose it was created from space. I don't know. Things that explode in space.
I suppose just heaps of gas built up, bang, got a planet. Same with the sun and everything else.
So you're saying it came out of some sort of
I'd
explosion?
say it would have been gas, yeah. Would have been an explosion.
And then after that, there was just a planet there? Or?
That's a really good question, actually. I suppose it would be a whole bunch of gases, and then bang, planet started evolving. All the gases were right.
Was there a particular explosion you had in mind? Perhaps one you learned about from a popular American sitcom?
From the Big Bang, maybe.
Yeah, the Big Bang.
The Big Bang Theory or something like that.
There was a bunch of dust that was formed during the Big Bang.
I've been to a couple of museums here in New Zealand, and then it all starts with the Big Bang, it says, and then you see a lot of volcanic action.
The Big Bang Theory. That's one of the theories of how Earth was created.
So the Big Bang created the Earth?
Yes.
It was like boom, and Earth was there. Now the trouble with explosions, which I was trying to hint at, is that they tend to blow stuff apart. They're more destructive than constructive, but what we're looking for is a mechanism to form the Earth, to bring things together. So how could the Earth form out of an explosion?
Masses that were then clustered together and compacted together and consolidated.
It was debris that gathered together through gravity.
Okay, where did that debris come from?
The Big Bang, I suppose, the original.
That big explosion led to a whole bunch of debris?
Yes.
And then it collapsed down
Exactly.
because of gravity?
Yes.
Now we're on the right track. The gravitational attraction between all mass is what causes matter to clump together into galaxies, stars, and planets. There's only one little problem. After the Big Bang, there were only two elements, hydrogen and helium, in the whole universe. So how could we form the Earth, including its oxygen, carbon, nitrogen, silicon, aluminium? I say it that way for my Australian viewers. How could we form all these other elements? Well, the truth is, the Big Bang didn't form the Earth, at least not directly. The Big Bang formed galaxies of stars. Let's focus in on one of these stars in particular, one whose contents will go on to form the Earth. In this star, the lighter elements are fusing together to form heavier elements, carbon, nitrogen, oxygen, and eventually all the elements up to iron. Now, when this star runs out of nuclei to fuse, it explodes. And out of that debris could form either directly our solar system or another star which then explodes and forms our solar system. So you could say the sun is a second or third generation star. And you might say, well, that would have taken a very long time to occur. And it's true. The Earth has been around for about 4.5 billion years, but the Big Bang happened 13.7 billion years ago. So if my arm span represents the time that the Earth has been here, then the Big Bang would be about here. You're doing a bang-up job, guys. So when people tell you that we're all made of stardust, they're not trying to be metaphorical or poetic necessarily. They're being literal. The iron in your blood was actually formed in the core of a star at millions of degrees. We and the world around us can only exist because of the elements that were formed in earlier stars.